In this video, what I'm going to be doing is I'm going to quickly revise stress and strain curves and how they relate to the Year 12 course. Now, we will have covered all of this stuff in Year 11. I have already recorded detailed notes on all of this stuff, so this is really just going through it very, very quickly. This could be particularly useful for you. Okay, so to start off with, we have this graph. When we have this graph, it's a stress-strain graph. If you look at testing, it's the very first link in my testing notes. Look for a picture of Sam Rockwell. You'll see a picture of you'll see the stress-strained experiment taking place. When you look at that, we need to label the axes. The first axis is stress. We know that stress equals force over area. That's the second most important thing you need to know in this course. You should know that. This axis, the horizontal axis, is strain or extension. So this offers force, this one is often extension, right? So in the video that you'll see, it actually refers to force and extension, but what we're going to do is we're going to convert that using the area and the original length. We're going to convert that into stress and strain. I want to remind you that strain can also be written as the change in length, delta L, divided by the original length. That's a better terminology. I like to use E though, because that way we get the Flee formula. You should be familiar with the Flee formula. Now the idea is here that we have, for this range here, we're pretty well a straight line. And that straight line, we can say that the strain is proportional to the stress. We can calculate what the stress will be because it's proportional. It goes at a fixed gradient. That gradient is called Young's modulus of elasticity. Now, if we write stress over strain, we get this over this, which equals E equals Flee. Now, the point is that it's only proportional up to a limit, right? We call that the proportional limit. It also happens to be the elastic limit. This is the area where if you keep loading it up, it's going to spring back. After that point, after you reach that elastic limit, you're going to start having permanent deformation. Permanent deformation is really important when you want to make a car. You want the shape to be, to hold its shape. You don't want to keep springing back to the sheet of metal. But the thing is, you can only permanently deform things so many times, and we want to make sure that our load never exceeds that point. Because when we do all our designs, we want to make sure we never exceed that point, because if we start exceeding that point, even just by a little bit, that will have continuous increases in strain to the point where eventually we'll have failure. I'm not going to go into the detail of that. I think it's a little bit beyond the course. I may have spoken a little bit more about it in Year 11, but the idea is that the residual stresses will keep, when you load to here, say if we load to this point in the graph, if we then release that load, it's going to come back here, and the next time we're going to have that as our permanent deformation, right? Deformation. And then the next time we start the graph, it's going to now start from this location, and it's going to do the same thing over again, but it's going to be shifted because of that permanent deformation. Eventually, you're going to hit the failure load a lot sooner. So that's why we always want to make sure that we design for the proportional limit. Now, we're going to talk about one exception in a second, but what we need to do is we need to be able to find the proportional limit. There are two different ways to find the proportional limit. In this case here, we have definite yield. Definite, I think that's how you spell definite yield. At this point, we can clearly see the bottom of this little bump on the graph. When we can see that little bump on the graph, that's what we use. That's the lower yield point. That is the absolute value that we wanted to make all our designs from. Now, the reality is we never actually use that value. What we do is we use a factor of safety, which in professional work is written as phi times that value. This is the shear force, for instance. So we'd say phi times the allowable shear compared to the scaled up shear. So we also increase the load and we decrease the allowable load. So we might say that this value here, we might take 80%, or for steel we can use 90%. We'll call that phi. Usually we use FSY, but in this case, that would be for steel. This is what steel looks like. You should be able to recognize that steel has that telltale definitive yield. Now, what do you do if it doesn't have definitive yield? In that case, you're going to use what kind of stress do we call this? It has a name, Samson?
Progressive.
Progressive, excellent. So this is progressive, and here we can't find the yield stress. What we find instead is we find the proof stress. Yeah. So how we find the proof stress is we look at the strain and we find 1% of the strain, we take 1/5 of that. Now, you could have 0.2% yield strain, you could have 0.1% improved strain, but the idea is we draw a line that matches the gradient of the curve Now maybe you find the gradient in the middle part if there's a little bit of a slight curve, but usually there's a straight line that we can take a parallel line that runs through. Typically in this course we use 2% proof stress, which is same as a strain of 0.002. Or if we use the example of a 200 millimeter bar, that would be a strain of 0.4 millimeters. We then draw the line parallel, and whatever value that is, that will be the value we use for our proof stress, and that will be what we use to design. We'll then probably put a factor of safety on that, and so then we'll have phi proof stress. Okay, there is a time when we don't use this. We use this for all of our calculations unless we are punching a hole in things. Normally, when we're designing for things, as soon as it starts to give up and say, I yield, I give up, that's where we stop. That's what we design for. We never want to work past that point because of the residual stresses that could cause failure. But if you're trying to punch a hole through things, it doesn't matter when it says it gives up. You need to punch all the way through, in which case we worry about its highest stress at all, which is called the UTS. Now, it's worth mentioning that all of these black lines that I've drawn here are what we observe as engineers doing an experiment. But sometimes scientists, they want to find the truth. They are willing to go, rather than us, we do all of our, in this example, we've used the same area, the original area for all of our calculations. Whereas scientists, they do the same calculation, they use the true area, and the true area will start to get smaller at this location. At this area, the cross-sectional area will be smaller because of what's called necking. So here we have the original A0 and it starts to get smaller, and when you start dividing by the true area, we notice that in fact the stress does go up forever, right? And so that's where we should be able to, there'll be HSC questions that ask us to differentiate between true stress and engineering stress. Now, obviously, what we're familiar with is engineering stress because it's functional. We're able to read these diagrams and get the information we need. But just so that we're fully aware that the internal stresses do continue to increase forever, scientists have demonstrated that there is in fact a true stress if you take into account that changing area. The last thing I'm going to talk about in this video is resilience versus toughness. So toughness, we're familiar with things like notch toughness, is a measure of impact resistance, how well it can withstand a sudden, how much energy it can take before it fails. Now in the case of toughness, what we're interested in is the area under the graph, how much crayon it takes to colour in this area. Whereas for resilience, this is how much it can take, how much energy it can take without deforming. And so often that's just as important for people in their designs, right? Once it starts to form, we have problems. So that's the difference. I did say that was the last thing. It's worth noting, and that we'll have other examples in the book, but we can tell other properties. We can tell things like how a brittle material looks like this, a ductile material looks like that. This has something that's very elastic looks like that. The strength is measured by how high the material is. So there's different things that we can measure. The stiffness is the level of how strict Young's modulus is, with how steep the gradient is. I think that's a pretty good summary of everything we need to know about stress and strain. And yeah, that will be it.
Don't forget to like and subscribe.